Hello students, in this video we'll see an example of how to use the rational root theorem to solve a constant coefficient differential equation with integer coefficients. So let's consider the following example. Let's consider the ODE. 3y triple prime minus 4y double prime minus 5y prime plus 2y is equal to 0. We can take this constant coefficient ODE and write it in our D notation. So we should remark over here that this is a constant coefficient ODE. So we can attempt to factor the differential form. Our differential form expression will be 3d cubed minus 4d squared minus 5d plus 2 applied to y is equal to 0. So the rational root theorem tells us that the possible rational roots will be plus or minus the factors of the constant coefficient over the factors of the lead. So the constant coefficient is 2, so in this case we'll have plus or minus, the factors of 2 are 1 and 2, over the factors of the lead, which are 1 and 3. So we have a collection of possibilities. We will have 1 over 1, so I'll have plus or minus 1, plus or minus 1/3, plus or minus 2, or plus or minus 2/3. So those are my 8 possible rational roots. So what we'll do is we'll plug in these roots and test to see if any of them work using synthetic division. So for example, we could test 1. So I will put a 1 in a box and store the coefficients of the polynomial next to it. So I'll have a 3, a -4, a -5, and a 2. And we'll do synthetic division, bring the 3 down. So that's the first step in synthetic division, is that the lead coefficient comes down. Then what you do with these terms is you multiply them. So you take the term inside the box and the term below and you multiply. And you bring that result over there. So I'll have a 1 times 3, which is 3. And then a -4 plus 3. So in this row, what we will do is we will add. So once we do this multiplication, we take these two numbers over here and we add them. And so when we do this, we'll have a -1. 1 times -1 is -1. This will be a -6, a -6, and a -4. Now the number we see over here is not 0, which tells me that 1 is not a root. So this implies that 1 is not a root. So we proceed to test other things. Now we can sort of plug in different values to see what things will and won't work. So for example, if I plug in -1, so now we can simply just plug in the values instead of using synthetic division. So if we plug in -1, what will we see? I'll have 3 -1 cubed minus 4 -1 squared minus 5 times -1 plus 2. So we'll do a quick accounting of this. This will be a 7, this will be a -3, and this will be a -7. So it looks like we will have a root over here. So we'll plug -1 into the box for synthetic division, and we will have a 3, -4, -5, and 2. And so I'll pull the 3 down. Then I'll have a -3, then I'll have a -7, then I'll have a +7, a +2, and a -2, and finally a 0. So in synthetic division, when we get a 0 down over here, that says that we have a root. So we can conclude from this testing of synthetic division that 3d cubed minus 4d squared minus 5d plus 2 can be factored. I can pull out a d plus 1 That is the root I found. And then the coefficients that are left over will become the coefficients of the polynomial. So those coefficients are what are the coefficients that are of the quotient polynomial. So I have a 3d squared minus 7d plus 2, and now that can be factored. So I will have d plus 1, and then a 3d, and then a d, and I can have I need to get a negative 7, so I'll put a negative 2 over here, and then I'll put a negative 1 over here, and we'll check. I get a negative d and a negative 6d and a positive 2, so it will work out. So our differential equation has the following factorization. Our differential equation is d minus 1, 3d minus 1, d minus 2 applied to y is equal to 0. And since it's a constant coefficient ODE, I can cycle these factors in any order. So note that these factors can be cycled in any order. And so what remains to do is it remains to solve the focus on the first term in the factorization and use the essential ODE to solve this. So if I focus on this term over here, what we will get is we'll get y equals c1 e to the 2x. And similarly, I'll have a c2 e to the negative x and a c3 1/3 x. So from this we can write down the general solution of our equation. It'll be c1 e to the 2x, which comes from this factor over here, plus c2 e to the x over 3, that will come from this factor over here, and then c3 e to the negative x. I have 3 constants in my solution. It's a third order equation, and we can check that these 3 exponential functions are linearly independent, so we can use our theorem to say that this function over here is the solution of our differential equation. Thank you very much.